Dear all, we are continuing with the properties of continuous time Fourier transform. The eighth property is differentiation in frequency domain. Okay, the statement is if the signal x of t is transformed to x of j omega, then t into x of t is transferred to j into d by d omega of x of j omega. That means if you are multiplying the original signal with t in time domain, then that would be equivalent to j multiplied with the first differential of actual Fourier transform. Okay, so we can prove this. For proving the statement, we need to start with the analysis equation x of j omega. Okay, so I am taking x of j omega. You know the equation is integral minus infinity to infinity x of t e raised to minus j omega t dt. Minus j omega t dt. Now, here you have first differential of x of j omega. So I am writing like taking the differential of x of j omega with respect to omega. Taking the differential of x of j omega with respect to omega, I can write this as equal to integral minus infinity to infinity x of t d by d omega of e raised to minus j omega t dt. Okay. Now, this will be equal to integral minus infinity to infinity x of t d by d omega of e raised to minus j omega t is actually minus j into t e raised to minus j omega t dt. Now, I can take this minus j outside. So, this will be minus j x of t minus j integral minus infinity minus j integral minus infinity to infinity. This t I can group with the x of t. So, t x of t e raised to minus j omega t dt. So, if you are taking the integral factor, you will be having the function t into x of t e raised to minus j omega t dt. So, actually, if you have a function here multiplied with e raised to minus j omega t dt, then this is giving the Fourier transform of that particular function. Okay, so I can write this as equal to minus j times the Fourier transform of t into x of t. Or I can write the Fourier transform of t into x of t is equal to, this minus j can be taken to the left hand side, so that becomes j times d by d omega of x of j omega. Okay, so if I am taking the expression corresponding to x of j omega and differentiating it one time using with respect to omega, then I will be getting the RHS as minus j times f of t x of t. Therefore, I can write t into x of t is transformed to j times d by d omega of x of j omega. Okay, so that is the property known as differentiation in frequency domain. Next, you have the conjugation property. So, you know what do you mean by a conjugate? If a plus jb is a number, then its conjugate is what? A minus jb. Okay, so the statement of conjugation property is that if x of t is transferred to x of j omega, then x star of t, that means the conjugate of x of t is transferred to the conjugate of its Fourier transform with all omega replaced with minus omega. Or I can say, in short, x star of t transferred to x star of minus j omega. Okay, so we can prove this. The proof is actually starting from the analysis equation again. So, take the equation corresponding to x of j omega, that is equal to integral minus infinity to infinity x of t e raised to minus j omega t dt. Okay, x of j omega is this. Now, if I am taking the conjugate of this particular equation, LHS become x star of j omega, that will be equal to the conjugate of RHS, that is integral over t from minus to infinity x star of t e raised to minus j omega star is e raised to j omega t dt. Okay, j omega t dt. Now, replacing every omega with minus omega. Replacing every omega with minus omega, I can write this equation as x star of minus j omega is equal to integral minus infinity to infinity x star of t e raised to minus j omega t dt. So here also you are getting the expression like a function into e raised to minus j omega t dt. That means this is the Fourier transform of that function denoted as x star of t. Or I can say the Fourier transform of the complex conjugate of a function is equivalent to x star of minus of j omega. So hence we can prove the conjugation property. The next property is actually convolution property. So convolution, you know, x of t convolution h of t is having an expression in time domain. So according to convolution property, we can say that the convolution in time domain is equivalent to or is transferred to multiplication in frequency domain. That is a statement of convolution property. Okay, so I am repeating, the convolution in time domain is transformed or is equivalent to multiplication in frequency domain. Performing convolution in time domain is equivalent to performing multiplication in frequency domain. Okay, so if x of the actual statement is, if x of t is transformed to x of j omega and h of j omega is the transform of h of t, then Fourier transform of convolution of x of t and h of t is equal to x of j omega into h of j omega. The meaning is that in frequency domain you can multiply the Fourier transform of x with the Fourier transform of h and take the inverse Fourier transform for getting the convolution in time domain. Okay, so we can prove this. We will be starting with the equation corresponding to convolution. So we know that let y of t is equal to x of t convolution h of t, and the equation corresponding to that is integral over 2 from minus infinity to infinity, integral over 2 from minus infinity to infinity, x2 h of t minus 2 d2. So this is the expression corresponding to convolution in time domain. Okay, so now I need to convert it into frequency domain. So I am going to take the Fourier transform of y of t, that is designated as y of j omega, that is equal to the Fourier transform of this whole equation. That means integral over t from minus infinity to infinity, integral over 2 from minus infinity to infinity, x of 2 h of t minus 2 d2 into e raised to minus j omega t dt. So this is the expression corresponding to this. So here also you need to substitute like t minus 2 is equal to p, or I can take dt is equal to dp. Okay, so if I am substituting that, I can write like this is equivalent to integral over minus infinity to infinity. This is actually 2 from minus infinity to infinity. Integral over t from this is t. Integral over 2 from minus infinity to infinity. x2 hp, because t minus 2 substituted as p, and e raised to minus j omega, t changing to, so from this equation I can write t is equal to p plus 2. Okay, so t changing to p plus 2, then dt changing to dp, and here you have d2. Okay, so here this particular term, if I am taking, this will be h of x of 2, this will be h of p. Here you have d2 term, dp term. This exponential can also be splitted as e raised to minus j omega p into e raised to minus j omega 2. Okay, that means I can write this as integral over t from minus infinity to infinity, not from t, it is from p, because we have substituted t minus 2 is equal to p, and therefore the integral variable changing from t to p. Okay, so integral over p from minus infinity to infinity, I am taking h of p e raised to minus j omega p dp, and that into integral over 2 from minus infinity to infinity x2 e raised to minus j omega 2 d2. Okay, this equation is actually x of j omega, and this equation is representing h of j omega. Okay, so I can write this as equal to x of j omega into h of j omega. Okay, that means the performing convolution in time domain is equivalent to performing the corresponding spectrum in frequency domain. The meaning is that if you have complex signals in time domain, or complex in the sense you have signals that are represented in a diverse manner in time domain, then if you are taking the Fourier transform of x of t and h of t, then the time domain convolution can be find out by multiplying the frequency spectrum and taking the inverse. You know how difficult is finding convolution in time domain. You need to go for graphical approach or equation wise approach. It is a time tedious process, but if you can find the Fourier transform of x of t and Fourier transform of h of t, take the product in frequency domain, you can simply take the product, then take the inverse by using the inverse equation, then you will be getting the time domain convolution. So that is the advantage of the convolution property. That is the most useful application of the continuous time Fourier transform. Okay, thank you.